Hey guys, what's up? This is your friend and tutor Manas, and it's going to be yet another session in this lecture series on engineering mechanics. Today we'll dive into the world of dynamics, and the topic that I'm going to talk about today is very special. It's work energy principle. Well, first of all, let me give you an intuition as to what this concept is all about, and for that we need to visit a gymnasium. Now let's take a look at this muscular fellow who is into some awesome workout. So here is this guy resting with his back and pushing this bar or weight upwards. And he'll continue doing so until he is absolutely exhausted. But whenever he pushes the bar upwards, work is being done by draining energy or utilizing energy or even expending his own internal energy, you can say. So the core idea of this example is to make you guys aware, make you guys understand that on our planet, nothing is for free. In order to get some work done, you have to drain some energy, you have to expend some energy, okay, or you have to utilize some energy that you already have. You can also say that this much amount of energy will be consumed to do that much amount of work. So essentially, work and energy are convertible, although there are some losses, okay, which is actually not a part of this particular video. Anyways, in today's video, we'll see the definition of work, and we'll also try to formulate work in terms of force and displacement. Then we'll go ahead and we'll actually compute the work done by the force of gravity and the force of spring. This will be followed by energy, and lastly, we'll learn the concept of work energy principle and how this can be applied to solve real life problems. So here we go. Let's kick off this session by understanding what exactly work means, right? So work is the energy transferred by a force. Let me just write this down. Energy transferred. Okay, energy transferred. So this is essentially associated with work. But if I were to explain you this concept in a very simple manner, it would be something like this. When force applied on a body, object, or even a particle causes it to move in a certain direction or even in the direction of motion, then work is said to be done. Okay, let me give you an illustration as to what this is all about. Let's say this is a plane surface, right? That's a plane surface, and in this surface let's have a block. Let me use a different color for that block. Let me use a green color. Okay, that's the block. Now what essentially we're trying to do is we're applying a force over here. Let's say that the name of force is F. Okay, so what this force does is, initially this was position number 1, and after the application of this force, the block changes its position. Okay, it moves towards the right hand side by a certain amount. How much is that amount? We don't have to worry about that, but it has moved towards the right hand side by a certain distance. Let's say this is referred by x. Okay, so this overall event is happening because of whom? Because of this application of force F, and this overall event is what you refer to as work. So whenever there is force and if there is some displacement because of this force, you'll say that work has been done. Okay, work is done. That's it. So let's go ahead with work of a force. Right. If we were to quantify work, for example, if I ask you that here is a block of 5 kgs, and if we can move this block say by a distance of 5 meters, can you tell me how much is the amount of work done? Okay, so right now we are not in a position to calculate or quantify work. In this part of the video, what we'll try to do is we'll try to formulate a relationship of work with force and displacement. So let me take a hypothetical case. Let's say we have a particle over here. Okay, let's say this is that particle, right? That's it. Now this particle has been acted upon by a force F. Let's say that the force makes an angle of theta with the horizontal, right? And this is the initial position of the particle, you can say. Okay, and the particle, on the application of this force, let's say that the particle moves towards the right hand side by a certain amount. Let's say dx, very small amount. Now where have we reached? We've reached here, this position. Okay, now this force, guys, is going to have two components. One component will be here, that is F cosine theta, while the other component will be somewhere here, and this is F sine theta. Let's say this is the coordinate axis, This is, that's x coordinate axis and that's y. Okay, now the amount of work done in taking the particle, okay, from this point to this point will be very small, that is dw, and it's going to be equal to the product of force and displacement. So how much is the force? If you can clearly see that the displacement has occurred in this direction, this is the direction of displacement, okay, or this is where the motion has happened, right? So the force responsible or purely responsible for the displacement towards the right hand side is F cosine theta. So what I'll do is I'll write F cosine theta over here multiplied by how much is the displacement, dx. So very small displacement corresponds to very small work, and let's just say that the particle started from here and it ended up, okay, over here. Let's say this is the initial position of the particle, okay, there was no movement, and at point 1 the force was applied, right, at a certain angle theta, then finally it reached here, point 2. In that case the total amount of work done would be obtained by integrating it from 1 to 2. Okay, same stuff, integrating this from 1 to 2. Let me choose a different color to write the final result. Let me use black color. Okay, so this is going to be very simple. This dw from 1 to 2 is going to be simply w, which is going to be equal to f cosine theta into, let me write this as f cosine theta. There is absolutely nothing, so nothing means 1, that is x to the power 0. Okay, and if you integrate this, this is going to be x to the power 0 plus 1 over 0 plus 1. So you are essentially left with x. Okay, and the limits you know very well from 1 to 2. So x is going to have limits from 1 to 2. So this is can be written as x2 minus x1, and this can be written as delta x, or the change in the value of x, right? Delta x. So guys, don't worry, this over here is x1 and this over here is x2 on a very general level. So this is the overall displacement from this point to this point, and that's delta x. So f cos theta dot delta x is the ultimate formula for calculating the work done. And whenever you're trying to figure out the amount of work done, always see where the motion is happening. So the motion is happening here in the right hand side direction, and the force dominating is F cosine theta dot delta x. In the vectorial form, it can be written as W is equal to F dot delta x, okay, which is essentially equal to F delta x cosine theta, right? So that's it. That's exactly how work can be quantified, and that's exactly how you can actually go ahead and calculate the amount of work done. Now, the example that I just explained to you was this. Let's say we have a block over here. Let's say that the block is 5 kgs, okay, and on the application of force, let's say we applied a force of 5 newtons. Thus block moved by a certain distance. Let's say that the distance is 10 meters, and if I were to ask you the total amount of work done in displacing this block of mass 5 kg, that can be calculated very easily. So W is equal to force, that is 5 newtons, okay, 5 multiplied by the displacement. How much is the displacement? 10 meters, right? And this is going to work out as 50. Now this is having a unit of newtons, so this is working out as 50 Newton meters, and Newton meter collectively is written as joules. Okay, so remember this, work and energy both are having same unit, so you can write this as 50 joules. Now there are some conditions which you can work out from this formula. So you have this formula in the form of work done is equal to F dot delta x dot cosine theta. So what if I say that theta's values was equal to 0? What will happen? Well, if the value of theta is 0, that means that the direction of force and the direction of displacement, you can say d, let's say, or x, whatever, both of them are headed in the same direction. That means the angle between them is absolutely 0. In that case, cos 0 will be equal to 1. So the work done in that case will be equal to F delta x, which essentially means it is a positive work. So guys, remember this logic. Force and displacement in the same direction, that means positive work. Okay. Secondly, if theta is equal to 180 degree. So what will happen is, if force is towards the right hand side direction, okay, then displacement is happening towards the left hand side direction. In that case, what we'll achieve is cos 180 is negative of 1. You'll have negative work. So W is going to work out as F delta x, but with a negative sign. So I'm writing that negative sign over here, right? So this is negative work. Remember, force and displacement in the same direction, that means positive work, and force and displacement in the opposite direction, that means negative work. And then finally we have this case, theta is equal to 90 degrees. Just put the value of theta is equal to 90 degrees over here. Okay, cos 90 is obviously equal to 0, so no work done. So it's something like this: if force is towards the right hand side, then x could be either upwards, it could be either downwards. In both the cases, you will see that the angle made, or the angle between the two, is going to be equal to 90 degrees. In that case, work done will be equal to 0. That means there is absolutely no work done technically. Now, there are plenty of forces acting on planet Earth, but right now we are interested in calculating the work done by the force of gravity. So here is the arrangement. Watch this carefully, guys. So let's say that's the initial position of the particle, and this over here represents the final position of the particle. Now let me tell you, this over here is representing a vertical plane. Alright. Now, somewhere along this path, this particle is moving somewhere along this direction, and finally it reaches this final position. Let's say we have taken this very small patch, say from P until we reach here, P dash, okay, and there is basically some horizontal as well as some vertical displacement. There is a horizontal displacement in the form of dx. This right over here is x, so parallel to this it's dx, and this is y, so this is the corresponding change in y. Now what we are essentially interested in is calculating the amount of work done by the force of gravity. Now this is the vertical plane, okay. Now the force of gravity will be actually acting in the downward direction, so it would be something like this way. Now we are assuming that the particle is having a mass of m, so the weight acting in the downward direction, okay, is going to be equal to mg, right? Okay, so here is the deal. Let me choose a different color. Let me use a black color. Okay, so very small amount of work will be done in carrying the particle from point P to point P dash. Okay, that small work done, let's say, is represented by dw, which will be equal to amount of force. So we are interested in calculating the work done by this force mg. So that's the force. We know the formula for work done is equal to force multiplied by displacement. And guys, just try to work out how much the displacement is. So ultimately, where is the object headed? The object is moving in the upward direction. That is for sure. That is certain. Okay, that is moving in the upward direction, right? So this dy comes into the picture. So this is the force mg and this dy in the upward direction. Alright, what's next? So we know this formula that work done is essentially a product of force multiplied by displacement multiplied by cosine theta. So if you watch carefully, force is acting in the downward direction, okay, dy, that is upwards. So both of them are absolutely opposite to each other. In that sense, theta will be equal to how much? It's going to be equal to 180 degrees, and cos 180, you know very well, is equal to negative of 1. So this is a negative work, in fact. So what essentially I can write over here is, okay, if I just write over here cos of 180 degrees, then dw will work out as negative of mg dot dy. And if you were to calculate the total amount of work done starting from this initial position, right, till we reach here, in that case we have to do an integration. Let me tell you what that integration is. Okay, so this is going to be y1, that's the initial positions, let's say 1, and this over here, let's say, is position 2 for the final position. Let's say this over here is y2. So if we were to calculate the total amount of work done by this force, that is the force of gravity, Okay, it would be something of this sort. You need to integrate this tw right from 1 to 2, and this over here again from 1 to 2, or from y1 from to y2. That's it. So this is going to be very simple. Here it is, w1 to 2. Okay, and this work done is for the force of gravity, FOG, force of gravity, is equal to, this is going to be very simple, minus of m g, this is going to be y. Okay, and if you put the limit from how much, from 1 to 2, it's going to work out as y2 minus y1, which can ultimately be written as delta y. So essentially I can write this work done from taking the particle from 1 to 2 on a vertical plane, okay, under the action of gravity, you can say. Okay, work done by the force of gravity is negative minus mg dot delta y. Okay, so let me simplify this further. If I can just extend this, keep on going ahead, keep on going ahead. Okay, if I can just make this dimension, yeah, this over here and this over here, this is how much, that's y2 minus y1. Watch this carefully. And y2 minus y1 can essentially be written as h, let's say, right? So we can write this formula as, again, work done in taking the particle from 1 to 2 by the force of gravity is equal to negative of mgh. That's it. So there is a conclusion. Let me zoom out slightly. So here it is, like this. This is basically conclusion which we can derive. Here it is, conclusion, and it's like this. So we are actually carrying this particle from bottom to top, and the work done by the force of gravity worked out with the negative sign. Okay, so the conclusion says work done by the force of gravity in carrying the particle from bottom to top will work out always negatively. Second conclusion is, this is conclusion number 1. Let's work out the second conclusion. If you watch carefully, now had the particle started with this point, okay, let's say this was the initial position and this had been the final position, that means from top to bottom, in that case this force of gravity and displacement, both of them would have been in the same direction. So in same direction the work done is always positive. In that case you would have got this from top to bottom, okay, under the action of gravity. In that case the force of gravity would have done some positive work, okay, because in that case mg would have been headed downwards, and also displacement, that is what delta y, in the downward direction. And here what happened was mg was in the downward direction and the displacement dy or delta y was in the upward direction. That's it. And when you speak of work done by the force of gravity in a horizontal direction, it's absolutely 0, because you know very well, when force is towards the right and displacement is either upwards or downwards, then the angle between them is how much? It's absolutely 90 degrees. And when theta is equal to 90 degrees, cos 90 is 0, and in that case the work done will be absolutely equal to 0. Okay, so that's done and dusted. Now let's try to figure out the work done by the force of spring. So here it is. That's it. Okay, now let me use a red color for explaining you guys. Okay, so this is the relaxed position of the spring. Okay, relaxed state of the spring, you can say, relaxed. Right, that's the position and that's the final position. What we're trying to do is we're trying to pull the spring, let's say by the help of this external force, and in that process the spring elongates by a certain amount, let's say by a very small amount, tx. Now guys, you should realize this. If you try to pull the spring towards the right hand side, the spring is going to pull you back, okay, by generating an internal force, and this is that internal force, F internal force, which I'm going to refer to as the spring force. I don't know whether you've heard about this or not, but spring force in general is FSP is equal to or is a product of Kx, and here K is referred to as the spring stiffness. Now for different springs there are different values of spring stiffness. For example, if I were to explain you what the spring stiffness is all about, let's say you go to a market and you purchase a spring having a spring stiffness of say 20 Newton per millimeter. That essentially means that in order to deform the spring by an amount of 1 millimeter, okay, either by compressing or by stretching, you need to apply a force of how much? That is 20 newtons. Now guys, remember this: any spring for that matter will have a different stiffness under compression and different stiffness under tension, right? So that actually is not a part of this lecture, but remember this stiffness is going to be different for tension and for compression, right? Okay, now by pulling this, some amount of work has been done, and what we're essentially interested in is calculating the amount of work done by this spring force. Okay, let's say very small amount of work has been done. So work essentially is equal to or is a product of force and displacement. So you can clearly see force is the spring force, and spring force is the product of spring stiffness multiplied by the deformation, and that deformation is over here, it's dx. So the total work done in pulling the spring, okay, from this position over here to this position is a product of the spring force, that is F of SP. Let me write this FSP, right, multiplied with the deformation. How much is the deformation? It's dx. Very simple. So FSP can be written as kx multiplied by this dx. So what we'll try to do is, let me write this one more time, TW is equal to kx dx. Now guys, watch this. Where is the displacement happening? Right hand side. Where is this spring force headed? Towards the left hand side. That means it's something like this. This is displacement, and this is the direction of force. How much is the angle? 180 degrees. So theta is equal to 180, cos 180 is equal to negative of 1. That means is a clear indication in fact that when force and displacement are opposite in direction, you get a negative work. So this has got to be accompanied with a negative sign. Let me put this, right? And now let's say for a particular range from say point 1, let's say from point 1 to point 2, from point 1 to point 2, okay, we are pulling this particular object attached to the spring. The total work done in that case will be equal to, let me integrate this. This is going to be very simple, minus of k, and this is going to be from, let's say, x1 to x2 x dot dx. Now guys, watch this, x dx. Let me integrate this term only. X ds is nothing but x square over 2, and we have to put this limit x1 to x2. Okay, let me shift this slightly towards the right. Let me have more space, and this essentially can be written as half of x2 square minus x1 square. Okay, so ultimately this integration will be from 1 to 2, dw will be equal to w1 to 2, and this is the force of spring that we're talking about, will be equal to we have this minus k times, okay, this is 1 by 2. So let me write 2 over here. This is going to be equal to x2 square minus x1 square, that is a square minus b square, a minus b, a plus b. So x2 minus x1, x2 plus x1. Okay, what we can essentially do right now is we can shift this a over here and over here also. In that case, we can write this once again as work done from 1 to 2 is equal to negative of, let me write this, negative of x2 minus x1 and kx2 plus kx1, and this 2 has been transferred over here. Okay, now guys, watch this carefully. This is nothing but force F2, and this is nothing but force F1. So you can clearly see F1 plus F2 divided by 2 is the average force. Okay, and this is the deformation or the displacement, whatever you can say. So work done essentially can be written as negative of the product of displacement, okay, multiplied by the average force, right? It's better that you write force side of displacement. So negative of average force into displacement. That looks far better. Force and displacement. Negative. You will always get a negative sign. I would suggest all of you to do this derivation once again by pushing the spring towards the left hand side. In that case, the spring in itself will generate a retaliating force in the right hand side direction. This F internal will be towards the right hand side. In that case, you can do the same derivation and you're going to get this same final result. So guys, that was all about work done. Now let's take this session forward and let's talk about energy. Well, the capacity to do work is energy. In very simple terms, or in layman terms, you can say if you've got a whole lot of energy and if you can somehow utilize that energy or focus that energy in the best possible manner or in the right direction, then you can extract a lot of work from that. Okay, you can have a lot of output in the form of work, you can say. Right now, energy is basically a scalar quantity. That means it has some magnitude. Unit is obviously joules, same unit as that of work done, but this energy is directionless. Okay, remember this. Now, work basically was a product of force and displacement, and you saw that force and displacement, both of them are vector quantities. So the product of two vector quantities is in fact a vector quantity itself, that is work. But here energy is absolutely directionless. The next point that I'm going to talk about is that energy has different avatars. Okay, or you can also say that energy can manifest itself in different forms. Well, you can take a look at mechanical energy, you can take a look at wind energy, you can take a look at thermal energy, heat energy, sound energy. A whole lot of energies are there on our planet. Okay, which can be utilized in the best possible manner and get converted into work. Okay, and as an engineer, it is our prime responsibility to make sure that maximum amount of energy can be utilized to produce output or to produce work. But the kind of energy that I'm going to talk about as far as this particular course of engineering mechanics is concerned is the mechanical energy, which essentially is a combination of, you can say, kinetic energy as well as potential energy. So let's kick off. First of all, let's take a look at this kinetic energy. And for that, let me explain this example to you. Here, we're having a frictionless surface in the form of a line. And what we'll try to do is we'll keep a block, say, having a mass m, right? And a force is acting over this block. Let's say this force is represented by simply writing F. Okay. So what essentially happens is this block sets itself into motion. And in that process, it will travel towards the right hand side by a certain amount. Let's say by a certain distance, you can say. Let's say that the distance traveled by the block is represented by small d, right? So this is where the block was at rest, and this state can be associated with motion, right? Having some velocity v, you can say. Okay, so what we're interested in is the energy transferred by this force, and you know very well that the energy transferred is the work done. So if you can somehow get the value of work done, you can somehow say that in fact reflects the energy, right? Now you know very well from the definition of work that W is equal to force multiplied by the distance traveled, or the displacement, you can say, and here it has been represented by small d, right? But from the definition of second law, we know that F for any object in motion, F can also be written as product of the mass of that object multiplied by the acceleration that block has acquired. So essentially, I can write this as W is equal to M into A into D. What does that mean? Well, let me go ahead with this. Now, you must have heard kinematic equations in the form of V equals U plus AT. You must have heard about V square minus U square is equal to 2AS. And you also must have heard about S is equal to UT plus half AT square. Out of these three kinematic equations, I'm going to be using the second one. I guess that was this one. V square minus U square is equal to 2A. Instead of distance, I'll write T over here. Well, all of you should know this, that U here represents the initial velocity. Okay, let me write this. As far as V is concerned, V represents the final velocity. Final velocity. And you know very well, initially the block was at rest, so the velocity is obviously going to be, let's say, 0 meters per second. Okay, and when the block was in motion, That's the final velocity, and here let's say it's represented by simply v. So what we'll try to do is we'll have this. Okay, you put the values 0 over here. So v square is essentially equal to 2 times of AD. And from here, what you can do is you can get the value of acceleration in terms of v and d, that is v square over 2d. What we'll try to do is we'll put the value of acceleration over here, and let's see what happens. Something beautiful happens. W is equal to m into a, and a is nothing but v square over 2d multiplied by, what's this? That's the displacement. D and d cancel out, and here is something which is very familiar, and something which has something which we have been studying throughout our 9th grade, 10th grade, and so on. Half of m v square, and this by definition, this half of mv square by definition is nothing but the amount of kinetic energy of the block in motion. Okay, so that was all about kinetic energy. Okay, here the motion was happening in a sort of horizontal sense, right? But as far as potential energy is concerned, what exactly you'll see is this. Let me make an example. Let me make this plane surface. Let's say we have a block over here which is having a mass of m. What we wish to do is we need to carry this block in the upward direction, right? Let's say over here. And what we wish to do is we have to calculate the amount of work done by this force in the upward direction. Let's say this is the force. Okay, in order to carry this block, let's say from position 1 to position 2. Now guys, you should know this. If this block is kept on ground, the earth is going to pull this object by an amount of mg, right? So the minimum force that you need to apply in the upward direction should be equal to how much? It's going to be equal to mg. Okay, so the block has to travel in the upward direction, okay, by a distance of say h, right? And if we were to calculate the amount of work done by this force, okay, in order to carry this block from position 1 to position 2, it would be something like this: force multiplied by the displacement. So displacement has happened in the upward direction, and the amount of displacement is nothing but h. So F can be written as m dot g, and this d can be written in the form of h. So that is essentially the work done by this force F in order to carry the object from point to point 2, right? And this by definition is nothing but the potential energy. Okay, now let me explain you in this manner. Let me choose a different color. It's something like this. Let's say this is earth, right? And you have a block over here. You had a block over here, let's say. Right now the block has been shifted to this position. Okay, so this right here, let's just say, is the final position. Okay, and this right here is the initial position. Now if I were to ask you the amount of energy required to transfer this block from initial position to final position, it would be something like this. If I say that this is the height h, okay, then the amount of energy required to transfer this block from the initial position to the final position will be amount of energy required to transfer this block from the initial position to the final position will be equal to how much? M G H, and this energy is nothing but the potential energy, right? That's it. Let's take one more example. Let's have some numerical values. Let's say we have a block over here, right here. Let's say this block is having a mass, say 10 kg. Okay, now this block, this is the ground. Let me write ground over here. So this block is at a height of, let's say, 10 meters above the ground. So if someone asked us what is the potential energy that this block is going to have in this position, right? Potential energy of the block, let's say in position 1. Well, this can be computed very easily. It's going to be equal to mgh. So m is nothing but 10, and let's just assume for the time being that acceleration, let's take it as 10 meters per second square into 10, right? G, and multiplied with the height. Okay, this is going to be 10. So essentially this is going to work out as how much? That's 1000, right? M, G, and H. Okay, if you were to work out the units, it's going to be something like this. M is nothing but kgs multiplied by acceleration due to gravity is in meters per second square. Okay, multiplied by H. What's H? H is nothing but this, meters, simply, right? This over here, right, guys, is nothing but newtons. So that's newtons, and this is nothing but meters, and Newton meters collectively, let me have some more space, Newton meters collectively can be written as joules. So this right here, this block right here in position 1 is having a potential energy of 1000 joules. Okay, but if somebody asks us, well, what happens if this block falls halfway, right? In that case, the distance that this block is going to have with respect to the ground is going to be how much? It's going to be 5 meters. So in that sense, let's say this is position 2. Potential energy at point 2 can be written in the form of, again, mgh. M is going to remain same. The mass of the block does not change. Okay, acceleration of due to gravity on planet Earth is fixed. Let's take an approximation as 10 multiplied by this distance. So this is going to work out as 5 times of 10, that is 50. 50 times of 10 is 500. Oh, that's strange. I don't know whether you have been able to work out this strangeness or not. And you can clearly see that there has been a drop of how much? 500 joules. That's interesting. Strange, isn't it? Now you guys must have heard about the conservation of energy, that, and something which I've been listening through 5th grade, 6th grade, that energy can neither be created nor be destroyed. It can only change its form, right? So this is pretty strange. Right here, the energy worked out as 1000 joules, and in position 2, the energy has worked out as 500 joules. That means there has been a drop of how much? 500 joules. So where is this gone? This is missing. And this is something that we're going to work out in the next part. Okay. Now guys, some of you guys must have worked this out, where this 500 joules is gone. Okay. And this is something that I will be taking up in the next part, where we'll see how potential energy can essentially be converted into kinetic energy. And that's exactly what I'll be working on. So now let me tell you what the secret is, why there was a drop of 500 joules. Okay, let me make another figure and let us shift to this figure. All right, this is better. Okay, so here we are. We have an object over here. You can clearly see this, and this has been lifted to a position 10 meters above the ground, you can see. And at that position, you can clearly see that the potential energy calculated is 1000 joules. Right, now let's say that the particle is somewhere at the center, like this, right? Let me make this randomly. Okay, that's fairly good. Now this is at a height of 5 meters. Okay, so what's the big deal? The big deal is we're going to calculate the potential energy in this position. Let's say this is potential energy at position 2. Let's say this is position 2, right? And if we were to calculate this potential energy, mass is going to be, we assumed it as 10, G we assumed it as 10, and height is going to be 5. So 10 into 10 into 5, 100 into 5 is 500. Now it's interesting, 500 joules. Okay, potential energy. Well, but what about the law of conservation of energy? What does the law of conservation of energy say or tell us? Well, it tells us that the energy in the entire universe is constant, or in other words, I can also say at each and every point the energy remains same, it does not change. But now this is very contradictory. You can clearly see that this particle over here had an energy of 1000 joules, but when it descends, okay, somewhere at position 2 only 500 joules of energy is left. So my point is, where is the remaining, okay, where is this remaining 500 joules gone? Why? Is this missing? No, it's not missing, man. I'll tell you what the answer is. This remaining 500 joules is nothing but the kinetic energy. Why is this the kinetic energy? because here the object was stationary, here the object was at rest at a certain height, and at that positionally the object will be acquiring some sort of potential energy, which worked out eventually as 1000 joules. Now half of that potential energy, that is 500 joules, has got converted itself in the form of what? Kinetic energy. That's it. That's the simple reason. And if you add this, potential energy at 2 is 500 joules, and the kinetic energy at 2 is also how much? This is 500 joules. So 500, let me make some more space. 500 plus 500 is again going to work out as 1000 joules. It's that simple. Now guys, let me take one more position. Okay, somewhere here, let's say this is going to be the third position, and let's say this is at a height of let me assume this has 3 meters. Now if I were to calculate the potential energy at this position, potential energy at 3 is going to be how much? Mass, what's it's 10, acceleration due to gravity assumed is 10 multiplied by 3. So this is going to work out as how much? This is going to work out as 300 joules. Again, the point is energy conserved. How much was initially the energy? It was 1000 joules. So at each and every point the energy should remain same. So my point is, where is the remaining 700 joules gone? That 700 joules is nothing but the kinetic energy of the particle at position 3. That's not 700 joules. Let me write that in a better way. 700 joules. That's it. At each and every point you're going to see that the summation of the total energy, right? Total energy Ke plus Pe, no matter where you go, at position 1, okay, and at position 2, Ke plus Pe, at each and every position. Okay, let me write this as Ke nth position and Pe nth position, as far as this particular example is concerned, is always going to work out as 1000 joules. You can work that out. That is pretty easy. So some part of potential energy always get converted into kinetic energy, and so on. And eventually when this block, where is the mouse? When this block hits the ground, or when this block is just about to hit the ground, at that point the value of h is going to be 0. So the potential energy here, let's say this is the 0th position, potential energy here the height is 0, is going to work out as 0, and the entire potential energy, you can clearly say, has been converted into kinetic energy, okay, at 0, which is going to work out as 1000 joules. And this is something that we have achieved by the definition of law of conservation of energy. Okay guys, now we'll work out what the work energy principle is. Here we go. So in order to understand this principle, what I'll do right now is that I'll consider a track over here, okay, a random path. Let's say this way, and we'll have a particle. Let me make that particle with what color? Let's say red color. So we have a particle over here. Let's say this position of the particle be represented by just randomly A1, okay, and this position of that same particle is represented by, let's say, this is A2, and somewhere in between, okay, or somewhere along this path, let's choose one more position. And by the way, the mass of this particle has to be taken as m. Okay, the mass of the particle has to be taken as m. Now what we're essentially trying to do is we are trying to bring this particle, say, from position 1 to position 2, and this particle does not move by its own, but some sort of force is acting on this particle, and this force is represented by this, given by F, you can say. Okay, now obviously this force is going to have two components. One be the horizontal component, and not exactly the horizontal component, but one will be the tangential component. Let's say that the angle made at this point, okay, at this point, if I can make a tangent over here, the angle made with that tangent is alpha. Then this particular force is going to have two components. One is going to be along this tangent this way, and let's say this is Ft. One more force is going to be this way, and let's say this is represented by Fn. All right. So what essentially we are trying to do is we are trying to develop a work energy relationship. Okay, so what is the force of the work? What is the work of the force rather? This force, it should be equal to the change in kinetic energy. That's the work energy principle, and I'm going to give you the proof in a sort of mathematical form. All right, so what we are essentially doing is that we have considered a particle of mass m, okay, which is being acted upon by this force F, right? And in that process it moves along a certain path. This is that path, and somewhere along this path we have taken a random position, and here we have taken the component of this force Ft and Fn. Okay, now let's say this is the arc, and let's say this is the center of that arc. So this is the normal force acting along the center of the arc, and this is the tangential force at this point on the curve, on the arc, whatever you can see. So we are interested in calculating the amount of work done in carrying the particle, say from position 1 to position 2, which eventually will be equal to the change in kinetic energy. Okay, so how can that be achieved? Here we go. Let me okay, now from the definition of Newton's second law, let me have some space. From the definition of Newton's second law, we can write this: F equals m, that is mass of the particle, into acceleration. Let's say we are interested in this force Ft, tangential force. So Ft is going to be equal to the mass into the tangential acceleration, right? Fair enough. And we know from the definition of acceleration that it is the rate of change of velocity. So acceleration can essentially be written as dv over dt. Rate of change of velocity is acceleration. Rate of change of displacement is the velocity. Okay, we'll see that also, don't worry. All right, so I can essentially write this. Where is the cursor? Here. M dot dv over dt. Okay, now guys, you have to watch this very carefully. This dv over dt can be written as a product. So dv over dt can be written as dv by ds dot ds over dt. So both this ds and ds will cancel out. dv by dt will remain. Okay, so this is exactly how we can write this dv over dt. And from the definition of velocity, we have this ds by dt. S is nothing but the displacement. So rate of change of displacement, okay, can be written as this. So essentially what I'm trying to say is that dv over dt is nothing but this v dv by ds, v dot dv by ds. So let's just write this down. This is going to be interesting. So tangential force F is equal to m dot v dot dv over ds. Okay, let's make some space. Here we go, and let us just shift this ds over here, and in that sense ft multiplied by ds is equal to m dot v dot dv. Okay, now what we're interested in is calculating the work done by this force. This force I'm talking about, this force in carrying the particle, say from position 1 to position 2. So for that what we need to do is we need to integrate, right, from s1 let's say to s2. Here also we need to do this integration, and here the variable is v. So in that sense, here let's say that the velocity is represented by v1, and at position 2 let's say it is v2. So the integration will happen say from v1 to v2. That's simple. Now guys, you have to look at this very carefully. Can you just tell me what exactly this is? I think after watching the lecture this much, you can actually work out what exactly this is. This is nothing but the work done. Okay, work done in what? In carrying the particle. In carrying the particle. Let me write this completely. Carrying the particle from position 1. Let me have some space. To position 2. That's it. Okay, that's it. Pretty good. So What is this work done? This is the amount of work done in carrying the particle from position 1 to position 2. Okay, who does the work? This force does this work, right? So on to the left hand side, we can replace this by W1 2. We need some more space. That looks good, which is going to be equal to m times of this is going to be a very simple integration. V dv is nothing but v square over 2. It has limits from v1 to v2. So when you put in the limits, it's going to work out as half of v2 square, okay, minus half of v1 square. So taking that 1 by 2 as common, let me write this: half of v2 square minus half of v1 square. So let me just write it over here: half of v2 square minus half of v1 square. And when this m enters inside the bracket, what happens is this actually becomes the formula for kinetic energy. This will become the final kinetic energy, that is at position number 2, and this will automatically become the initial kinetic energy, that is at position 1. So let me write this: half of m v2 square minus half of m v1 square. Okay, so let me rewrite this again. Work done in carrying the particle from position 1 to position 2 is equal to half of m v2 square, that is kinetic energy at 2. Okay, let's say this is represented by t2, and let's say this over here at position number 1, this kinetic energy be represented by t1, and this is essentially equal to t2 minus t1. That's the work energy principle, my friends. Very interesting. Okay, so there are certain notes which you can actually make from this formula. The first one is that this work energy principle can be applied for Newtonian frame of references only. For Newtonian frame of references only, right? Where the velocity of frame of reference is equal to 0. But realistically, if you think, there is nothing in this cosmos, nothing in this entire universe which is absolutely static. Just think about this. If you are watching this video right now, can you assume that you are absolutely static? No, you are not static. Why? Because you are actually a part of this earth, and earth is rotating about its own axis. The earth is also going around the sun, okay, and the sun is going around some other galaxy. So there is absolutely nothing in this universe which is absolutely static, and that is why came the concept of the theory of relativity, that is Mr. Einstein. And if you're an ardent follower of Mr. Einstein, then you should realize that there is absolutely no frame of reference in this world which is absolutely static. So all the experiments that we conduct on planet Earth are assumed to be done in the environment of a Newtonian frame of reference. Okay, that is assumed to be having zero velocity. That's it. That's the first point. So what's the second point? Well, this is pretty interesting. Second point is, let's say initially the velocity was 0, v1 is equal to 0, and finally there was some velocity. In that case, initially the kinetic energy will be again 0, and finally there is going to be some kinetic energy that is going to be equal to t. In that sense, what we are essentially trying to indicate is this: okay, here the velocity was 0 and here there was some velocity. In that sense, what we are essentially trying to indicate is this: the work done from carrying the particle from the state of rest to a state of motion, or from a state of 0 velocity to a state of some v velocity, is equal to t, that is half mv square. Okay, so in order to bring a particle, say, from 0 velocity to a velocity v, the amount of work done will be equal to the change in kinetic energy. Not exactly change in kinetic energy, but half of mv square. Simple. Now there is one more interesting thing that we can actually work out from this work energy principle, and this says, let's say initially there was some velocity, and let's say finally somewhere traveling along this path the velocity kept on decreasing and finally it became 0. In that sense, you will have some initial kinetic energy. Let's say it is equal to t, and final kinetic energy, since the velocity is 0, is going to be equal to 0. So in that sense, we have this as a final formula: negative of half of mv square. You can just work this out. This is going to be pretty simple. It's going to be equal to negative of T1 because T2 is 0, negative of T1. So negative of T1 is nothing but half of mv square with a minus sign. Why have we got a negative sign? Because it's a case of retardation. Okay, the velocity kept on decreasing, right? And then secondly, if I were to explain this mathematical formulation in a sort of statement, it would be something like this. In order to stop a particle, say which initially has a velocity v, okay, in order to make sure that that particle's velocity becomes 0, the amount of work done will be equal to negative of half of mp square. That's it. So that was all about work energy principle, and in the next section we'll take up a few examples and then we'll try to see how this work energy principle can be applied to essentially calculate the velocity, and that is something which is extremely important and which you should never ever think about missing. See you in the next section. Now let's try to understand the work and energy principle with the help of this simple example. So guys, this essentially represents the two different positions of a bob which has been attached to this string over here. So what essentially we're trying to do is we are left in this bob. Okay, let's say this is position A1 and this over here, let's say, is position A2. And what we wish to calculate is the velocity of the bob. Okay, this circular fellow is the bob in fact, at position 2. So how can that be achieved? Well, we've got to work out. Okay, and this is something that we'll be achieving with the help of this work energy principle which we have learned right now. Now let me use a different color. Let me use a black color. So essentially, somewhere along this position, this bob was here. Okay, and if I were to tell you the force acting on this bob immediately, which is primarily responsible for the movement of the bob in the downward direction, it would be this weight. Okay, and let's just assume the weight to be represented by simple small w in the downward direction. So here it is. This is position 1 and this over here is position 2, and according to the work and energy principle, WEP, the mathematical formulation is this: work done in taking the particle from position 1 to position 2, that is W1 to 2, is equal to the change in kinetic energy, that is final kinetic energy T2 minus initial kinetic energy T1. And here guys, this is the initial position. Bob was at rest. Okay, I'm writing this over here, at rest. In the state of rest, velocity is obviously going to be equal to 0. So if the velocity is 0, that clearly means that the kinetic energy initially will also be equal to 0. So we are left with only this fellow, that is this T2, that is the final kinetic energy. Okay, and the final velocity over here is something that we are going to work out. Let's say that the velocity over here is v2, and let's assume that v2 is equal to v, as simple. So the force acting in the downward direction is what? W. Work is nothing but a product of force and displacement, W multiplied by the displacement. So length of the string, assume it to be equal to L. Okay, so if you watch carefully, this was initially the position of the bob, and this right here is the final position of the bob. And if we can just work out the amount of descent that has happened, okay, the total downward movement of the bob is nothing but equal to L. So, and this particular force W, which is actually the weight of the bob itself, is essentially responsible for the total downward movement. So W has to be multiplied with L over here. So this is essentially the work done by this weight W. That's it, which is going to be equal to the kinetic energy, and kinetic energy is half of m v2 square, but we are assuming that v2 is equal to v, so half of mv square. So you just need to solve this equation, and then finally you can actually compute the amount of velocity that this bob has in position 2. Okay, the velocity of bob in position 2. So this is going to be pretty simple. V square can be written as 2 W L over what shall I write, over m. Now guys, I'm pretty much sure that you must have gone through this formula. Watch this. W is equal to mg. Being a student of engineering or being a class 11th grade or 12th grade student, you must have gone through this formula. Weight is a product of mass multiplied by the acceleration due to gravity on planet Earth. Had you been on a different planet, the acceleration due to gravity would have been slightly different. So G can be written as W over M. weight over mass. So weight over mass can be replaced with this g over here. So essentially v square can be written as 2 times of gl. And if I were to say the velocity of the bob, okay, where is the cursor? Velocity of the bob right at position 2, it is going to work out as root over 2 gl. That's the final nail in the coffin. So guys, that was all from my side for today. Well, if you've got any doubt or query, do write them down in the comment section below. I'll be very happy to answer them. And if you believe that this video tutorial has helped you enhance your knowledge of engineering mechanics, then do share and like this video, subscribe to this channel, and also press the bell icon so that whenever I upload a new video, you get a notification, you get an update. Well, needless to say, I'm going to be back with more such videos on mechanics and drawing. Until then, it's a wrap. This is Manas Patnaik signing off. Take care, have a great day, and keep learning.